Greetings to respected faculty members and my dear friends. Today we are going to present our mini project titled Artificial Analysis of Memory Efficient Attention Mechanisms Using FlashAttention. I am Shaheli Paul, 24 BCE 0562.
This is Ipsita Jena, 24 BCI 0157.
Hello everyone, my name is Ankita Banerjee and my registration number is 24 BCI 0125.
Now I will go on and introduce our project. This project is based on the subject Computer Architecture and Organization and focus on how efficient memory usage plays a critical role in improving performance of modern algorithms. In today's world, deep learning models, especially transformer-based architectures, are widely used in applications like chatbots, translation systems, and image processing. However, as these models grow larger, they face serious challenges related to memory and performance. In this project, we analyze these challenges and study how FlashAttention provides an efficient solution. To understand this problem, let us first look at the attention mechanism used in transformers. The attention mechanism helps the model focus on important parts of the input. It works using three matrices: query, key, and value. The model computes relationships between all elements in the sequence, which requires generating a large matrix. The issue is that this matrix grows quadratically with sequence length. So, if the input size increases, the memory requirement increases very rapidly. This becomes a major limitation for large-scale models. So the main problem we are addressing is standard attention mechanisms consume a large amount of memory and are inefficient for long sequences. This leads to high DRAM access, memory bandwidth bottlenecks, poor cache utilization, increased execution time. From a computer architecture perspective, this happens because the algorithm performs excessive data movement between memory levels. As a result, the system becomes memory bound, meaning the performance is limited by memory speed rather than computation speed. To solve this problem, we need to understand memory hierarchy. Modern systems have registers, shared memory, cache, and global memory. Accessing global memory is expensive, so efficient algorithms try to minimize global memory access and maximize usage of faster memory. With this understanding, I will now hand over to my teammate to explain the solution using FlashAttention.
FlashAttention is an optimized algorithm designed to reduce memory usage and improve performance. The key idea is tiling or blocking. Instead of computing the entire attention matrix at once, the input is divided into smaller blocks. Each block is processed separately. Intermediate results are stored in fast memory. This improves data locality, cache utilization, memory efficiency. Another concept used is kernel fusion. This combines multiple operations into a single step, reducing intermediate memory storage. So, FlashAttention focuses on optimizing data movement rather than just computation. Now let's look at the implementation. In standard approach, we compute matrix multiplication between query and key, apply softmax, multiply with value. This creates a large matrix in memory which is inefficient. In timed attention, we divide the input into smaller chunks, process each chunk separately, store only partial results. For example, instead of processing 1024 elements at once, we process 64 elements at a time. This ensures that data fits into faster memory usage is reduced, performance improves. So we replace one large computation with multiple smaller efficient computations. This approach reflects real-world FlashAttention. The key benefits are reduced global memory access, better use of shared memory, improved performance for large inputs. Now I'll hand over to my teammate who will discuss the result and conclusion.
Thank you. Building upon the previous explanation of attention mechanisms and FlashAttention, I will now present the results and analysis of our project. We conducted experiments using different sequence lengths 128, 256, 512 and 1024. From the results, we observed that for smaller input sizes, both standard attention and tiled attention perform almost similarly. However, as the sequence length increases, standard attention becomes significantly slower and its memory usage increases rapidly. In contrast, tiled attention remains more stable, consumes less memory, and delivers better performance for large inputs. In some cases, we also observed that standard attention may fail due to memory limitations, while tiled attention continues to function efficiently. These results clearly highlight the importance of memory optimization in modern computational systems. Now moving on to the advantages and applications of flash attention. The key advantages include reduced memory bandwidth usage, improved cache utilization, and the ability to efficiently handle long sequences without requiring any hardware changes. Flash attention is widely applicable in areas such as large language models, natural language processing systems, speech recognition, and computer vision transformers. To conclude, this project demonstrates that performance improvement is not only about faster computation but also about efficient memory usage. Standard attention mechanisms are often limited by memory bottlenecks, whereas flash attention improves performance by reducing data movement, applying timing techniques, and effectively utilizing the memory hierarchy. The key takeaway from our work is that understanding computer architecture is essential for optimizing modern algorithms. Thank you.